my recording back on. And I'm gonna backtrack just a little bit and do a balancing reaction problem. That was one of the things that we did on Tuesday. All right, let's see if I really wish I had subscript capability here. Actually, okay, let me do it this way. It's probably going to be way more wobbly, but let's see if I can do it this way. So if we have CS2 and we are adding to that some oxygen gas, and our products are going to be carbon dioxide, so CO2, and some SO2. So one of the things that we need to look at here is we definitely have some mismatches just to start off with. If you look here where the oxygens are on the right-hand side, we've got 2 oxygens in the carbon dioxide, but we also have 2 oxygens over here. So my first attempt at balancing this is to go back and make a correction to my oxygen molecules. So I'm going to do this. I'm going to put a coefficient of 2 out in front of my oxygen molecule, and that will solve some of my problems. That will actually give me enough oxygens in order to at least superficially address the fact that my oxygens didn't match. All right, so that kind of sort of looks like it's beginning to solve the problem, but it is more complicated than that. If you look over here on the left-hand side where we have CS2, okay, I've got 2 sulfurs. That means I'm going to need a minimum of 2 sulfurs back on the right-hand side. So again, this is me tinkering back and forth with trying to achieve an optimal way to balance it. So right at the moment, I'm going to leave that 2 there, and I'm probably going to have to go back and change my coefficient. This will give me CO2, and then I'm going to have 2 sulfur dioxides, so 2 SO2s. All right, gets me a little closer. Okay, now I have 1 carbon each side, 2 sulfurs each side, but now I'm back to the problem of my oxygens don't quite match. I need to total them up. I've got 2 that are here in my carbon dioxide, but since I have 2 molecules here in my SO2, I really actually need to go back and change change the coefficient in front of my SO2. So I'm gonna see if I can use my erase function here. All right, and now I'm gonna go back and change it so that it will give me a match, hopefully. And then you go back and you double check. So 1 carbon, 1 carbon, 2 sulfurs in the CS2 molecule, but I have 2 because there's a 2 out in front of my SO2 over here on the right-hand side. 6 atoms of oxygen. On the right-hand side, I have 2 in my carbon dioxide and 2 times 2 in my SO2 molecules there. So once it's fully balanced, I have 1 CS2, 3 oxygens, 1 CO2, and 2 sulfur dioxides. I just randomly picked a place to start, okay? You can start wherever seems the most logical, and then you tinker back and forth in order to shoot for having a balanced equation. All right, let me switch back to my notes file. All right. The last thing we were talking about on Tuesday had to do with the rules of solubility. And we made use of the nitrate rule, which allowed us to eliminate the magnesium nitrate as a possible precipitate. Even though they might touch temporarily in order to meet a possibility of being a precipitate, they are not going to stay stuck together. So that one got eliminated. My chloride rule has exceptions. And we ultimately made use of one of those exceptions as part of the solving of that problem. All right, let's move on to the next example. So this one involves mixing sodium sulfate and lead 2 nitrate. And again, I'm kind of asking the same two questions of, did I get a precipitate? And if so, what did I make? Now, sometimes the answer to did I get a precipitate, if you're in the lab, relies upon an observation. If we're doing this on paper, we're actually more interested in following the rules for this. So split your sodium sulfate into its component parts. Keep in mind that sulfate does not fall apart into separate sulfurs and oxygens. Nitrate does not fall apart into separate nitrogens and oxygens. So my pieces that I have available here are sodium and sulfates and leads and nitrates. So this goes back to the first and last, third and second. I'm going to try to switch back over here and do my whiteboard thing again. All right, so we have sodiums, which are +1s. We have sulfates, which are -2s. We have a lead of the +2 variety. My little widget here is being slightly uncooperative. And I have nitrates, NO3 minus. All right, so first and last, third and second, okay? Keeping in mind that when you create these molecules and you write them down, the positive ion must be at the front. You cannot write SO4 PB. You have to write the lead at the beginning of your options there. So let me flop back over to my notes. All right. So my two options, the things that might have created a precipitate, are lead sulfate or sodium nitrate. Now I put this set of 6 solubility rules into a separate file, which I believe I loaded onto the page that says handouts. So the first one we've already touched on. Yeah, I know it says most nitrates are soluble, but we can kind of expand that to say pretty much all nitrates are soluble. As freshman chem, we are unlikely to see an exception to the rule for the nitrates. Now, the second rule says most salts that have sodium, potassium, or ammonium are soluble. And let me fix my subscript here. NH4 plus. So if your molecule starts with one of those three, it is really unlikely for it to make a precipitate. We've already touched on the chloride rule. There are three notable exceptions to that chloride rule. There are also three notable exceptions to the sulfate rule. This time, barium sulfate, potassium, not potassium, brain fart. Barium sulfate, lead sulfate, and calcium sulfate are your three notable exceptions. Now, the bottom two rules are kind of backwards in the way they are stated. So most hydroxides are not soluble, except for the sodium, potassium, and calcium. You can almost, okay, one of the things that's happening here is these rules are kind of order of importance. Basically, if you got all the way down to rule number 5 or 6 and you haven't eliminated something already, then you're down to the, well, what do I have left? Concept. Sulfides, carbonates, phosphates, and chromates are generally not soluble. All right, so back up to the lead sulfate thing. So let me switch back over. All right, so I made lead sulfate as one of my possibilities. The other possibility being sodium nitrate. So look at your second molecule here. Look at your sodium nitrate. You can eliminate this as a possible precipitate using either of the first two rules, okay? You can look here at this bit here that is the nitrate end and go, oh, well, okay, it can't make a precipitate because it's got a nitrate in it. Or you can also eliminate this possibility by looking at the first end of it here, which is where the sodium is. That's the second rule. Most sodiums, potassiums, and ammoniums are soluble. So for two different reasons, it can't be this one. So go back and look at this one. It's like, okay, we've got a sulfate, and it's a noticeable exception. This is the identity of your precipitate. I did make a precipitate, and it was lead sulfate. So keep track of the rules. The rules are of great use. Now, how about if I mix iron sulfate, this is specifically iron 2 sulfate, and some sodium nitrate. Okay, first and last, third and second. But pay attention to your charges. And I just realized I have a goof. I have iron 2 sulfate, and I put the wrong subscript here. This is supposed to be a little 2. Yeah, I screwed that up. So my two possibilities were iron 2 nitrate, so first and last, or sodium sulfate. So I start going through eliminations. Okay, so it's probably not this one, okay, because it's nitrate. Okay, nitrates, we're saying don't make precipitates, don't make solids. But if I go over and I look at my second one, okay, it starts with a sodium, so that means it's probably not a solid. And even if I look at the end of it where the sulfate is, it's not one of my exceptions. You will note that of all of the problems, if you're looking at, especially if you're looking at end of chapter problems, and the lab that is coming up called metathesis, that sometimes, maybe on the order of 15 to 20% of the time, you get no precipitate at all. Okay. Then we hit my notable exception thing here that usually somebody, especially when we're in class, somebody goes, ooh, but what about this? So in reality, it is possible to actually get two things precipitating. For this semester, we're going to pretend that doesn't happen. There are additional rules, including something known as KSP values and differential precipitation, that become relevant in the second semester in Chem 112. For the moment, we're going to kind of ignore this. As I have said sort of before, chemistry tends to be taught as this sort of build where in the beginning you're told just kind of take it on faith, just believe that's the way it is, okay? And then the further we get into each topic, the more we realize that some of the things that you are in the beginning are told are absolute rules, aren't quite as absolute as especially the first semester tends to imply. So we need to be able to write some equations for all of these precipitation reactions. There are three main categories of equation. The first one is called molecular, and then there is complete ionic, and then there is net ionic. I will say that of the three, the middle one, the complete ionic one, I won't call it unimportant, but I will say it is of somewhat lesser importance than the other two. All right, so let's kind of work our way through this. All right, so a molecular equation tells you kind of a little bit of everything, and it also gives you AQs and S's, something we talked about back at the beginning of this chapter. If I have iron 3 chloride, this is an aqueous solution, which means it actually, we know it falls apart in the beaker. I have sodium hydroxide. Again, this is an aqueous solution. Using my rules, I determined that iron 3 hydroxide is the one that is my solid. And then sodium chloride are my leftovers. And table salt, sodium chloride, we know is soluble in water. So also pay attention to your coefficients here. I have one molecule of FeCl3. I have 3 of the sodium hydroxides, because otherwise I don't have enough OHs to match up with my iron atom. And then that also gives me 3 sodiums along the way. to help match up with my 3 chlorides that were back from that first molecule. So I wrote it and I balanced it, and this is the end result. So the middle one, the second of the 3, is known as the complete ionic. It's longer to write out, but it does have some nice features to it. One of the things it does is it shows you everything that is ionized, and it shows you what those charges are. The only exception to this being the one that didn't fall apart. So the FeOH3, that's your solid, is the one that stays stuck together. And so when I write a complete ionic, it is the only molecule that does not show its charges. Make sure you are keeping track of both charges and coefficients. So looking across my complete ionic here, I have 1 atom of iron, but because I had 3 sodium hydroxides, I have 3 sodium ions, and I have 3 chloride ions, and I have 3 hydroxides. My sodium and my chlorides don't have a different format on the right-hand side. They're identical. They look like they have a charge on the left-hand side, and they look like they have a charge on the right-hand side. We're going to call them something specific. We are going to call them spectator ions. Okay. The Euro Cup is going on right now. Scotland plays Sweden, I think it is, tomorrow. I haven't been watching the games. I've just been sort of watching the score. Wales tied. I'm a Wales fan. Wales tied against, I believe it was Italy. So if you're in the stands watching, you're a spectator. Okay. So that's kind of what's going on here in the molecule, because in this particular reaction, the sodiums and the chlorides are just kind of hanging out, bopping around the beaker, okay, or the test tube. They're not doing anything. They're there. They're watching, so to speak. They are not part of the actual reaction. So what if I got rid of my spectator ions? I crossed out my sodiums on both sides and deleted them, and crossed out my chlorides on both sides and deleted them. Your leftovers. Your leftovers give you a net ionic. Now, for a precipitation reaction, you will see that all of the net ionics kind of bear a resemblance to each other. They have something that is a cation plus something that's an anion on the left-hand side. And then they have a unionized, fully assembled molecule on the right-hand side. And that is kind of a predictable pattern to the net ionics for precipitation reactions. All right, let's kind of look through another one without quite so many intervening commentary here. So if I have calcium chloride and potassium sulfate, okay, those are my 2 reactants. What happened? So my molecular equation, again, stick with that idea of first and last. So the calcium will try to stick to the sulfate. Third and second. Yes, I know I have 2 potassiums and 2 chlorides. And let me show you something that people are often very tempted to do that is unfortunately wrong. For many things, this is the most common error. People do this. They go, oh, well, I have 2 and 2. Okay. No, unless you have a mercury atom involved, a mercury 1 atom, you are not allowed to do this. Your 2 must come out to the front as a coefficient, and you lose both of your subscripts that way. Coefficient, not subscripts. Let me show you. This is the only molecule that you are likely to see in first semester that violates this rule, and that is mercury 1 chloride. Remember, mercury's weird in every way, shape, and form. It's a metal, it's a liquid, all those things. Mercury 1 always travels with a buddy, and it is the only scenario where you can have a duplicated subscript. Anything else, no. All right, so we had calcium chloride, or calcium sulfate. We have potassium chlorides. So I'm going to write my complete ionic. I'm going to split apart everything that was not a solid, that did not stay stuck together. So my calcium, and I show its +2 charge, as well as its 2 chlorides. You cannot leave the 2 as a subscript. It cannot be Cl2 with a 2- above it. Okay, the 2 has to go out in the front. It has to do with the way we looked at it on Tuesday, where the calcium is the blob in the middle and the chlorides are on either side. There's one on the left and one on the right, more or less. Same thing is true here with your potassiums. Don't leave it as a subscript. It's got to be a coefficient. Now, SO4 is a polyatomic. Okay, polyatomics don't fall apart in water. Here's my precipitate, because using my rules, one of the rules said most sulfates are soluble, but not not barium, lead, or calcium. So here is my notable exception. And then here are my leftovers. My 2 potassiums and my 2 chlorides, they might bumper car together, but they're not going to stay stuck. If I get rid of everything that is the same on both sides, then I have my leftovers. 1 cation and its accompanying anion makes a neutral molecule. Like I said, they all have this similar profile. Now, one of the things that's true also, as far as the upcoming lab is involved, is you are, at least if you have me for lab, I am going to have you write a molecular and a net ionic for each of the 11 reactions. This means there are 22 equations for that particular lab. Usually people do them on a separate sheet of paper. I have a report page that you are allowed to use in order to make sure you have the right number of equations that I believe I loaded to the lab module for Canvas, or you could just simply do them on paper. It doesn't matter which way you're doing them, but you do need all 22 equations. So one of the things we mentioned was, okay, sometimes there's no precipitate. So here is an equation that is a molecular equation. I have potassium nitrate and sodium chloride, but everything is aqueous. If I want to go back and put a little additional information in here to make it a little bit more obvious. All right, so my potassium nitrate is aqueous, my sodium chloride is aqueous, but then over here on this side, I also have aqueous sodium nitrate and aqueous potassium chloride. If there is no precipitate, you can write a molecular. I could potentially write a complete ionic, but there is no net ionic at all. If you did not make a precipitate, you cannot write a net ionic equation for that reaction. I will tip you off, one of the 11 reactions that we do in lab specifically is designed to generate no precipitate. Get a little bit of a color change. Not much, but a little bit. But there is no cloudiness or precipitation in that particular reaction. All right, let's skim through a couple more here just so that you're kind of getting an idea on how this sort of flows together. If I have silver nitrate and ammonium carbonate, I've got several different polyatomics going on here. Pay attention to your polyatomics. Make sure you're not cutting them in half. I made silver carbonate and ammonium nitrate, specifically 2 ammonium nitrates. Back to that rule of you can't have double 2s. You can't do NH42, NO32. That's not allowed. My middle there is the one that has everything ionized. I've got silver with its little +1 charge. I keep running into things that glitched when I did some copy pasting from some other files here. This is supposed to be a subscript, NO3 minus. Ammonium, 2 of them, carbonate. All of those things are ionized on the left-hand side. The one thing, okay, this actually uses the last rule. This uses rule number 6. Rule number 6 said most sulfides, carbonates, phosphates, and chromates are not soluble. So this one actually makes use of that final 6th rule. But ammonium nitrate is soluble for 2 different reasons, okay? It's soluble in part because it's a nitrate, but it's also soluble because it starts with an ammonium. And then the third segment there. Get rid of the things that are identical on both sides, which are your spectators. And now you have leftovers. You've got a silver and a carbonate, actually 2 silvers and a carbonate, and they stick together and make one neutral molecule there on the right-hand side. All right, so, and I'm gonna actually not go through this one. Part of my notes are actually designed for me to like write things on the board and like give you guys like 5 minutes to work on it, and then I talk about the answers. So sometimes I have more examples than I might otherwise give out. So go back and read through that one. It follows the same basic patterns. Another thing that this one in particular though, utilizes is the idea of the phosphates. Okay, again, we're kind of picking on rule number 6 here, in terms of which one is the precipitate and which one is not. All right, let us take about a 10-minute break, and then we will come back and talk about acid-base reactions. And I will be back in about 10 minutes. So how much did my half gallon of skim milk cost? But yeah, so I wanted to make sure I had some. Yeah, I still have a little coffee. So yeah, my cake is not as fluffy as I think it should be. I think the oil is a factor. And then can you also grab up the bits that you chopped off and tote them around and shove them in the plastic bag that is beside the garage door? Because there should be a half full bag around there.
So it's got a little too much oil in it. She thinks. Squash. Yeah.
So we have tomorrow off. Well,
Because
thus
of the
far we
Fed.
think that we have tomorrow off.
Okay.
Although it's actually been signed. It's supposedly signed at 3:30. So I was telling everybody, just make sure. So I went to.
Yeah, lots of conversations going on in my background. So we have covered basically all of the main bits of the precipitation reactions. Like I said, this is a really big, chunky chapter that has a lot of information in it. I'm kind of hoping to get at least into gas generating reactions, if not through them. We definitely won't get through redox stuff tonight. So begin to, if you haven't turned in chapter 3's homework, make sure that comes in tonight. Begin to look at chapter 4 homework over the weekend, because it is kind of a big bunch of information. And you don't want to leave it all kind of to the last minute. All right, so let us switch over to acid-base reactions. So when we were doing the nomenclature part, we had some rules of nomenclature that were specific to acids. And one of the things that we kind of said was that if it starts with an H and it's not a water molecule, then we are making assumptions that it's going to be an acid. One of the things that you also hopefully began to pick up on a little bit as we went through some of the acid naming is that some of them have a single hydrogen at the beginning, some of them have 2, and some of them have 3s. And there is some terminology that applies here. And again, this is somewhat in terms of inorganic chemistry. There are some additional things that if you take higher levels of chemistry, that they will talk about, oh, there are some additional options, but we're going to sort of confine ourselves to certain things for this semester. If you see 1 hydrogen at the beginning, we are going to refer to that as a monoprotic acid. Okay, mono for 1, because remember back to prefixes from the nomenclature end of things. Protic, because if you have a naked hydrogen, one that is missing its electron, all you really have left is a proton. So this is why they are calling it protic. Diprotic. So 2 hydrogens, sulfuric, oxalic. There's a handful of other ones which we've run across. There are a few that are triprotic. The one you are probably likely to see the most often being phosphoric, which is H3PO4. And from a inorganic chemistry point of view, there is no such thing as a quadra or tetraprotic. You're not going to see anything that has 4 hydrogens at the beginning of the molecule. Like I said, there are, if you dig deep enough into chemistry, there are some options, EDTA being one of them, a molecule that we addressed briefly in 2nd semester. And there are a few other really weird ones that pop up that do exist, but they're not really inorganic chemistry. They are either organic or biochemistry level. So we have seen bases without actually calling them bases up to this point. They are things that generate or release hydroxide when you dump them in water. So the 2 that we see the most of, and these are the ones we use in lab the most often, are sodium hydroxide and potassium hydroxide. To give you some reference points against reality here. So sodium hydroxide is the main component of Drano, the stuff that you use to open a clogged drain, whereas potassium hydroxide is if you don't have a self-cleaning oven or you actually need it to remove other things. I have a little tale to tell you here in just a second. Potassium hydroxide is the main component in such things as easy off. So a few years ago, I removed the wallpaper, which I did not install, that came with the house, in my kitchen. One of the things that the wallpaper involved was one of those things they call the chair strip or whatever, right around waist height. There's a strip that kind of runs along the wall horizontally. Well, I had gotten most of the other wallpaper off, and that particular strip, I swear, it was like it had been super glued to the wall. So being a chemist, I started with seeing if I could soak it with a sponge with water. Yeah, no luck. So I moved one step up. I used a weak acid vinegar, acetic acid. Yeah, that didn't really do a whole lot. Somebody suggested to me that Downy fabric softener was good for removing stubborn wallpaper. And I don't usually use fabric softener, but I went out and bought a small bottle and took a stab at that. So as I was working my way up in power, it's like, okay, so we've done a couple of different acids, so let's switch over to bases. So I ultimately ended up using my can of Easy Off oven cleaner to remove the wallpaper from my wall in that particular area, because it was the only thing that worked. So better living through chemistry. So one of the things that you will see here as we are looking at acid-base reactions is the number of H's on your acid should equal the number of OHs on your base, and that should equal the number of water molecules. So have a look here at the first one. We have acetic acid, vinegar, and sodium hydroxide. So we have a single hydrogen on our monoprotic acetic acid. The fact that there's hydrogens in the middle of the acetate is not actually relevant. We have one OH on the end of our sodium hydroxide. We made one water molecule. And the leftovers create an aqueous salt, in this case known as sodium acetate. So let's look at a diprotic one. Sulfuric acid has two hydrogens out in front, but I'm using some lithium hydroxide. Actually, not lithium hydroxide. Actually, I skipped down too many rows there. Some potassium hydroxide to neutralize this. I need two molecules of it, because otherwise I would not have enough OHs to cancel out with my H's from the beginning of the acid. I get two water molecules. And the salt that I make this time around is potassium sulfate. Look at the last one here, our somewhat rare triprotic acid. I use some lithium hydroxide, which is actually not super soluble, but I could make it work if I stirred my solution. And three OHs, okay? The big three out in front, make sure that I have three OHs to match the H3 at the beginning part of my acid. Look at your waters. I have three molecules of water. And this gives us then as a salt, lithium phosphate. So as a general trend this semester, we can make this statement. An acid plus a base gives you water plus a salt. Now, okay, look at your three examples there. It's like, none of them are actually sodium chloride. None of them are table salt. They are all a salt, meaning that they are an ionic compound. One odd thing that is true about acid-base reactions is, as long as we are sticking with strong acids and strong bases, we can assume that we always get the same net ionic. Once you get rid of the spectators, which for the first one would be the sodium and the acetate, for the second one would be the potassium and the sulfate, for the third one would be the lithium and the phosphate. If we get rid of our spectators, all we have left over are the H's, the OH's, and the water molecule. But, okay, we still have kind of a similarity, okay? One of the things that I've been sort of pounding on here about the precipitation reactions is that when you write your net ionic, you have a positive thing and a negative thing, and it makes a neutral molecule. That actually hasn't really changed. My cation is my hydrogen, my anion is my hydroxide. In this case, my neutral molecule, instead of being a solid, is a water molecule. So all of those are things that are ways to keep track of acid-base reactions. We are going to be doing some labs, some titration labs that involve neutralization, canceling an acid out with a base, or you could do it backwards. You could cancel out a base with an acid. All of those are referred to as neutralization reactions. We are going to be doing titration of hydrochloric acid solutions in experiment 9, and you're actually going to be titrating vinegar as your acid with some sodium hydroxide for experiment 10. And actually, I don't remember if, okay, I will not swear that this is actually the right thing. I have changed editions of textbooks so many different times. I don't actually remember if page 140 is in truth the correct edition for this textbook. Go back and check at some point. Look at your PDF file, or if you actually have a paper copy of the textbook. I can't remember if I corrected it to match the current textbook, or if this is a leftover from a previous edition. So keep that in mind. So now we're going to segue to the next segment. This is the one I'm going to end with tonight. Like I said, we're not going to get into redox until Tuesday. Gas generating reactions sometimes make visible bubbles. Sometimes the gas generation is more subtle and it just sort of fizzes a little bit without so much in the way of bubbles. If you take a metal carbonate or a bicarbonate and you add an acid to it, let me change my subscript here. So I picked on sodium bicarbonate. Okay, this is the stereotypical, I'm in middle school and I'm making a volcano reaction. So sodium bicarbonate is baking soda. Okay, that's what it's actually made of. And vinegar, acetic acid. When you add those two things together, this is not an acid-base reaction. This is a gas-generating reaction. I get a metal salt. So the metal that was on the front end of my carbonate, and then the anion that was on the back end of my acid. But I also get carbon dioxide and water. So this is kind of new, okay? The ones that we've mostly been looking at thus far have only had 2 products. Many, not all, but many gas generating reactions have 3 products. Now you'll see the one below it only has 2. This is why I said many, not all. Metal sulfides with acids give you hydrogen sulfide gas, stinky rotten egg smell, as its gas that is produced. And again, you have leftovers, okay? We still got to have balanced reactions. We still got to keep track of what we started with. So if I look at magnesium sulfide, so here is your metal sulfide. This time I'm adding hydrochloric acid to it. And I put my 2 in there so that this is a balanced reaction. My metal salt is my magnesium chloride. And this one does not have a 3rd product. My 2nd product, my gas, if I go back and put a little subscript in here to tell you, to remind you that this is where the gas is. Hydrogen sulfide is what's being produced. What if instead of a sulfide, you had a sulfite? So this time I have SO3. I'm still adding acid to it. I picked on hydrochloric acid again because it's pretty common. Metal salt. So the lithium from my original molecule is going to interact with the chloride from my hydrochloric acid. My SO2 here, this is my gas. And this is another one that has a 3rd product. Water is a byproduct. Now the final one, this one's kind of different in that when you're looking at the first 3 here, all of them are something and acid. Using ammonium, NH4, you need a base to make this react. So again, metal salt, that's a common theme here. Here's your gas. NH3 is the gas that you are producing. So I've got ammonium chloride. That's the same molecule that we sublimated in the separation of a mixture lab by heating it over the Bunsen burner under the hood. We've got our strong base, potassium hydroxide, and here's our products. Here's our metal salt, KCl, our gas, and water as a leftover. So again, kind of looking for themes here. In the acid-base reaction world, you have acid plus base gives you salt plus water. There's some themes here that are similar, but because the thing that we are using an acid or a base, we're not getting just 2 products. For most of these, we are getting 3 products, one of which is a gas. We're going to do a couple of gas generating reactions as part of the metathesis lab that's upcoming. something else that kind of falls in with this, and this is kind of actually where I'm going to end here, is being able to look at reactions and kind of have an idea where you're going with them. Classifying them is sort of what we're talking about here. Can I look at it and tell something about the reaction based upon the way it looks? So if I look at the top one there, the one that starts here with potassium carbonate. So I've got two things on the left-hand side, both of which are aqueous. Neither of them is obviously an acid or a base in any way. When I look on the product side, ooh, I see something that's a solid as well as an aqueous molecule. So having two separate things here that are both aqueous and one of your products being a solid, part of that is your tip-off that this is a precipitation reaction. Looking at the one below it. Well, I've got an acid, but this isn't really a base. Not really. It's a salt. A metal salt. A metal carbonate salt. Look at your products. I've got three separate products, and one of them is a recognizable gas, which is your carbon dioxide. So this gets us about 60 to 70% of the way through the chapter. We will dig into redox in a fair amount of depth on Tuesday. My husband, when she came in, was like, blah, blah, blah. Okay. If you have Friday classes, I believe the website for TCC has posted a formal reminder that tomorrow is the Juneteenth federal holiday, which is a new holiday this year. And so if you happen to have Friday classes, keep that in mind, that there are no classes being held tomorrow. And then since we have Monday, Wednesday labs for Chem 111, in about another week and a half, we get hit by the 5th of July as a federal holiday. So there's a bunch of gaps that are occurring kind of the way this semester is dispersed. So kind of keep that in mind. Questions about homework that's due tonight?
I have a question.
Yes.
On number 9, for finding both the empirical and molecular formula, when I was trying to figure out the molecular, I got a number a little bit higher than 1, but not 2. I don't know.
Let me twist around and grab my binder.
Yeah, I don't know if I did it right or not.
It should be, because I usually try to design them so that they're pretty straightforward. It should, if it's close to 1 within a 10th or so, you should be able to then make an assumption.
It's not for what I got. It's a couple tenths away. Yeah.
For number 9, the cadaverine?
Yeah, that one.
It sounds to me like a math error. It should be really, really close.
I mean, I don't want to tell you what I got, but I mean, I'll tell you what I did.
Because, okay, think about how we have been doing empirical formulas. First, you must divide. First, you must assume, okay, Your percentages are all going to convert over to gram weights because we must assume we have 100 grams of a sample.
Hmm.
Okay, that's your starting point. Then you have 3 elements. You have carbon and hydrogen and nitrogen,
Yeah.
and you have periodic table weights.
Yep.
So once you do your division, it should give you masses, or it should give you moles. And then you must do the ratio step.
The mole weight over the empirical weight, correct?
No.
No. Okay.
Okay. You must ratio your lowest number of moles to all of the other available numbers of moles. Sounds to me like you skipped a step.
Yeah, I'll probably have to redo that.
There is a relatively decent example in the notes that involved 4 different elements. I gave you one that had carbon, hydrogen, nitrogen, and oxygen. That's the one that you should use as your example for doing that problem.
Okay.
So see, yeah, it sounds to me like you skipped a step.
Okay. Well, I'll redo that one then.
Yeah, that problem should have a when you're trying to make a decision about empirical versus molecular, it should come out really super close to whole numbers.
Okay. I definitely didn't get that the first time. I'll go back to it now.
Yeah, sounds to me like you skipped one of the final steps in the problem.
All right. Thank
Other
you.
questions?
No, I'm good.
Okay. Questions about lab? I think everybody has done. This week was hydrate lab. Is there anybody who hasn't done the hydrate lab yet? I think everybody did that this week. Okay, so keep in mind that in the hydrate lab, there's a page for the report sheet, but there's a second page that's called the addendum that asks you to figure out how many molecules of water are attached to your substance. So when you get ready to finish out the math for that lab, make sure you have both pages. And people who have me for lab, there's 2 post-lab questions on that. Okay, we're still trying to figure out what's going on in terms of the college and whether or not we can all do labs together, A group and B group, but I haven't received any data yet implying that they've made a decision. So the limiting reactant lab, I need to actually activate that. I created it. I borrowed some stuff from Mr. Wheaton that he took pictures of. Over this weekend, I will probably turn that page on. That one is designed to be a remote, a fake lab, just an example lab where we're going to give you some data. You're going to do the math for it. I will probably actually spend a little time on Tuesday kind of coaching you a little bit in the direction of where we're going with that. Actually, we haven't done stoichiometry yet. I'm out of sync. We did balancing. We're doing reactions. Stoichiometry is at the end of the chapter. I might actually hold off on that. But that's an upcoming lab because I think the B group people are supposed to be technically doing that on Monday. If you're lost and you don't know where to start once I open up the file, just hang on to it. I kind of wish we could push it off one day of lab, but because we miss a Monday for the 5th of July, that makes it kind of problematic. And in case anybody else is unaware, I think I talked to both my Monday people and my Wednesday people. If you're somebody who doesn't have me for lab, it is possible / probable that after the 4th of July, when the governor rescinds the social distancing thing for Virginia, that lab, not lecture, we're still doing this for lecture, but lab, we may be combining A groups and B groups in order to have everybody be able to do the remaining 5 labs in the semester for real. So kind of keep that in mind. We'll try to keep everybody up to date. I haven't seen any hard and fast, yeah, we're doing it this way, this is what the schedule is going to be. I will tell you flat out, though, that since most of you have me for lab, the very last lab of the semester, the one that is designated atomic and molecular structures, we are going to bump that by a class period to actually make it. I'm looking to figure out what I did with my binder, my other binder. I will eventually post a reminder about this, but the schedule as printed implies that all of us are Zooming atomic and molecular structure on the 26th of July. We are going to bump it one day. Well, one lab day. Okay. We'll Zoom if we're still not face to face. We will Zoom on the 28th for lab. If we all are able to be in the same classroom, we might actually have it on the 28th, same day, have it on campus so that everybody can actually build the molecules. Lots of people get a lot of benefit from being able to put the Tinker Toys together and kind of see the molecule as they are having to draw pictures of it. We'll see what happens. I'll try to keep you guys up to date on that. Also, forewarned, this also probably means that in the fall, they are probably going to go back to having most science classes back to lecture in person. At least that's what they're hinting at us to, which I think is probably good for most people. Questions? Otherwise, I will turn on the limiting reactant lab here in the next day or so, and see people in lab on Monday for the metathesis lab. Bye.
Okay, thank you.